Stoichiometry is a quantitative approach to determine theoretical amounts of either reactants or products in a chemical reaction. Gravimetric stoichiometry, which is the topic of our video today, is used to determine masses or amounts in moles of either reactants or products. Now there are three different approaches to gravimetric stoichiometry. We have number one, moles to moles. Number two, mass to moles. And finally, number three. Now before we actually move on to an example, we need to know the steps. Let's go through them quickly. You can solve a stoichiometric problem in 3 easy steps. Step 1. Write a balanced chemical equation. Step 2. Write your given values. Finally, step 3. Use unit analysis to solve for your unknown. Example 1. Moles to moles calculations. The question reads as follows. Water decomposes into its elements. How many moles of hydrogen gas are produced if 0.5 moles of water is decomposed? Now, to solve this problem, we're going to follow our steps. Step 1, we're going to write a balanced chemical equation. The question states that water decomposes. So start out with H2O on our left. And show it splitting into its 2 elements. We'll see this isn't balanced, so we'll add a 2 here and a 2 here to balance out the sides. Now we move on to our second step. Write out our givens. In this case, they tell us we have 0.500 moles of H2O. Finally, we're going to use unit analysis to solve for our unknown. Now in this case, if we read the question, our unknown is the amount of hydrogen gas that's being produced. And using step 3, we can solve for this. We'll start with our given here. Now, the cool thing about our chemical formula is it gives us a molar ratio. We know that for every 2 moles of H2O, we have 2 moles of hydrogen gas. Therefore, if we have 0.5 moles of H2O, we will end up with 0.5 moles of H2. That's your answer. Alright, next, for example 2, we'll be doing a mass to moles calculation. The example reads as follows. Iron burns in air, reacting with oxygen gas to form the black solid iron 3 oxide. If 5.6 grams of iron are completely burned, how many moles of iron 3 oxide are formed? Now, if you'll recall, the first of those steps is to write out our chemical equation, so
Looking at the problem, we see we're going to have iron on our left side, followed by oxygen, and it's going to form iron oxide, which is Fe2O3, if we balance the charges. Now we're not done yet. Before we can complete this, we need to balance both sides. Let's start with Fe. Right now our Fe's are balanced. But we'll see here that if we balance out our oxygens, we'll have to change that Fe to a 4. And that leaves us with a balanced chemical equation with 4 iron on each side and 6 oxygen on each side. Next, we'll move on to step 2, which is stating out our givens. Now, if we look back to the question again, we'll see we have 5.6 grams of iron. So we'll put that down. Finally, we're going to move to step 3. Looking back to the problem, we see we are solving for moles of iron oxide that are formed. So we're going to use our given, 5.6 grams of iron, and solve for that. So to start, we put out our 5.6 grams. We're going to multiply by the molar mass ratio of iron, which is 1 mole is 55.85 grams, which you'll find on your periodic table. Next, we'll multiply by the Roller ratio between iron and iron oxide, which is 2 moles of iron oxide for every 4 moles of Fe. And that'll leave us with moles of iron oxide. Moles cancel out, grams cancel out, and all that's left is to put it into our handy-dandy Casio. Now, in doing this, make sure to remember sig digs. If we look back to the problem, we see we only have 2 sig digs. So although we get an answer of 0.05013, our actual answer is going to be 0.050 moles of iron oxide. And that's example 2. All we had to do is those exact same 3 steps that we can apply to all the different problems. Now let's move on to example 3. In this one, we're just adding one extra step because we're going from mass to mass rather than mass to moles. To start, we're going to write out our chemical formula once more. We'll see we have aluminum oxide on our left, or Al2O3, and it's going to decompose into its elements, aluminum and oxygen. Once more, we're going to see that for this to balance out nicely, we're going to have to balance both sides. So we're going to need 2 aluminum oxides, 3 oxygen, and 4. Next, step 2, write out all our givens. We're given 2.04 kilograms of aluminum oxide. So we will write that down. We can use that to solve for unknown. Next, we're going to put that to use. We'll write out our 2.04 kilograms of aluminum oxide. Just like in the last problem, we're going to multiply by our molar mass ratio in order to find moles of aluminum oxide. So look in your periodic table, add together the molar masses of 2 aluminum and 3 oxygen, and you will find the molar mass of aluminum oxide, which is 101.96 grams. Next, we'll multiply by the molar ratio between aluminum oxide and the pure aluminum, which we're solving for. For every 2 moles of aluminum oxide, we will produce 4 moles of pure aluminum. And finally, we're not done yet. We're going to convert that to grams. So for every 1 mole aluminum, we're going to have 26.98 grams, which once again you'll find on your periodic table. And all that's left is to put that into your calculator. 2.04 kilograms times the 1 mole of aluminum oxide over 101.96 grams of aluminum oxide times the molar ratio, 4 to 2, and finally by the 26.98 grams per mole. That's going to give you 1.079 kilograms of aluminum oxide. Because you have to remember we didn't cancel out that kilo at the start, so that's going to carry through. Now finally we have 3 sig digs, so that's going to be 1.08 kilograms of aluminum. And that is your final answer. Thanks for watching this video of Centennial Academy.